All right, some really quick problems here. We want to know what the voltage is that is necessary to force the following electrolysis reaction to occur. Here we're given our balanced redox reaction and a list of standard reduction potentials for those reduction half reactions there. All right, so for these electrolytic cells, you got to be on the lookout. It's going to be a little different from your voltaic cells. All right, so if we take a quick peek at the balanced redox reaction here, I'm going to very quickly throw in my oxidation states here. It's -1, +2, 0, and 0. So in this example, it is our copper ion that is going to be reduced. It's going to be gaining electrons, and it's our iodide ion that's going to be losing electrons. Now, the reason why that's important is because when we're doing these standard cell voltage calculations for voltaic or galvanic cells, we pick the most positive reduction potential to indicate the thing that was being reduced. But because it's an electrolytic cell and we're forcing the reaction to happen, you can't use that nifty little rule. So as we look at the redox reaction here, again, we decided that it was copper that was being reduced. So this is our reduction half reaction. And so when I rewrite this, I'm going to keep that half reaction the same. But this time I have to reverse that first reaction, even though it has the greater positive reduction potential, because again, it's an electrolytic cell here. So we're going to get 2I. I2 plus 2 electrons. Again, since we reversed it, we are going to reverse the reduction potential here. When you combine these two reactions, your electrons will drop out. And we have our original redox reaction. Our cell potential is going to be negative 0.20 volts. Now, a couple of just very quick things here. Our standard cell potential for this electrolytic cell is a negative value, and that's different from our galvanic and voltaic cells. Remember, the negative sign is going to imply here that it is non-spontaneous or non-thermodynamically favored. In other words, we have to apply this voltage to this system in order to get the reaction to occur. All right, problem number 2. This next type of question is a common one that you'll see with electrolytic cells, in which we are going to work with some charge and current and try and figure out a specific mass in grams that will be plated out as we perform this redox reaction. So let's take a look here. It's asking us how many grams of copper can be reduced by applying a 3.00 amp current for 16.2 minutes to a solution containing copper 2 ions. Okay, so our formula that we want to use is Q equals I T here. Q, of course, being our charge in coulombs. The current here is 3.00 amps, and we apply that current for 16.2 minutes. It's important, though, to change this to seconds, which would be 972 seconds. When we multiply those two values together, we get 2,916 coulombs. I'm going to give myself a little reminder here for sig figs that I should only have 3 sig figs in my final answer. Once we know the charge in coulombs, we can simply take that value, 2,916 coulombs, and divide it by Faraday's constant, or 96,500 coulombs per mole. And that will give us moles of electrons. And so a quick division here will give us 0.0302 moles as our moles of electrons. As we think about how much copper can be formed from the reduction of copper 2 ions, We need to write our reduction half reaction, which would look just like this. And then we're going to apply a little bit of stoichiometry to solve this problem. We've got our 0.0302 moles of electrons. As we think about where we're going next, I want moles of electrons to cancel out. I'm going to go to moles of copper. The relationship in our reduction half reaction is for every 2 moles of electrons gained, we're going to get 1 mole of solid copper. And then in order to get the mass in grams, we're just going to use our periodic table to get moles of copper to go from moles of copper to grams of copper. And 1 mole of copper is 63.54 grams. And a quick calculation here will give us 0.960 grams of copper that has plated out by applying 3.00 amps of current for 972 seconds. Boom. Okay, and our final problem here today, we're going to be looking at the electrolysis of water, or the splitting of water into its component elemental gases. We are asked to determine here the volume of hydrogen and oxygen that is produced when we apply current of 4 amps for 12 minutes. We're going to assume the volumes are measured at standard conditions, which is nice, so we can use that 22.4 liters per mole. As we look at the formula for the electrolysis or the splitting of water, we're also provided with the 2 half reactions here, the oxidation half reaction and the reduction half reaction. The very first thing we want to do is solve for the charge. To do that, we're going to use our formula Q equals I times T. Our 4 amp current here, 4.00. Our time, again, is in minutes. We need to convert that to seconds, which is 720 seconds. And so our charge in coulombs is 2,880. Quick reminder there for sig figs. Our next step is to determine how that relates to number of moles of electrons. To do that, we're just going to take the 2,880 coulombs, divide that by Faraday's constant of 96,500 coulombs per mole. That'll give us our moles of electrons. When we do that, we get 0.0298 moles of electrons that have been transferred in this electrolytic reaction. All right, and the final thing we need to do then is relate that number of moles of electrons that have been transferred to the oxidation and reduction half reactions to determine the volumes of our hydrogen and oxygen gases that were produced. So if we take a quick look here, if 0.0298 moles of electrons were transferred, for determining volume of oxygen, for every 4 moles of electrons lost, we're going to form 1 mole of oxygen gas. And because we want the volume of the gas, we need to do one more step here, moles to liters. Because we're at standard conditions, 22.4 liters is 1 mole. When we solve this, we end up with 0.167 liters of oxygen gas. However, we're also asked for the volume of hydrogen gas, which you can figure out a couple of different ways now that you know the volume of the oxygen gas that was produced, but we're going to work it through from the moles of electrons that were transferred in this electrolytic reaction. This time, however, we need to look at the reduction half reaction, and for every 2 moles of electrons gained, we get 1 mole of hydrogen gas. We do a quick conversion here between moles to liters since we're at STP. And when we do that, we get 0.334 liters of hydrogen gas. You also could have looked at the stoichiometry of the complete reaction here, you're going to have twice the volume of hydrogen gas as oxygen gas produced. And so you could have just doubled your initial volume, or your volume of the oxygen gas. And that's it for today.